Hi everyone, thanks for coming to talk. I'm Zheng Jie from Duke University. In this video, I will present our paper, Understanding Queries by Conditional Instances. First, let's see a motivating example from the classroom setting. In database courses, instructors often give exercise questions to students like this one. For each beer liked by a drinker whose first name is Eve, find the bars that serve the beer at the highest price. There can often be some errors in student submissions. And here we show one wrong query with two popular errors. The first error is in the string comparison for the first name. And the second error is that the query uses a self-join, and thus it will find bars serving the beer at not the lowest price instead of the highest price, while the correct query uses not exists. In this case, how can we explain these two errors in the wrong query to the students? In this work, we use conditional instances to explain the differences between the two queries Q1 and Q2. Conditional instances are adapted from C tables in incomplete databases, where the tuples include constants and label nouns. Here, for simplicity, if a label noun only appears once, we will replace it with the don't care symbol. There is also a global condition in the C instance, which is the conjunction of atomic conditions. Here, this instance I0 captures the mistake that the wrong query would return not the lowest prices as long as the instance has three different prices. We also show another C instance I1 with only two different prices, but its condition captures the error in the string comparison. In short, these two C instances explain the two mistakes in Q1 compared with Q2. More generally, we can consider the difference between Q1 and Q2 as a single query. Then, our goal is to characterize the query Q by showing different ways how Q would return non-empty results, or say how the query Q is satisfied using C instances. This is useful not only in helping explaining why queries are different, but also for helping developers understand how queries execute on different data and build test suites. Previously, people have been looking into finding concrete instances as counterexamples for two queries. For example, the concrete instance I0 prime here captures the same mistake as this instance I0. This can be generated by our previous solution based on a given test instance, or by tools like Cosette that generates counterexamples from scratch. As you may see from the concrete instance, there can be too many details that prevent the users from easily understanding the errors, while the instances can abstract away unnecessary details and show the important logic when the query would return different results. Moreover, these prior works did not consider how to capture different ways to satisfy the query. And finally, even if we adapt the prior works to search for all possible instances to capture different ways to satisfy the query, there could be infinitely many satisfying instances. To this end, we propose a framework using C instances to characterize queries. The first question we need to answer is, what is a good characterization for a query Q? Given a set of C instances, one can have these basic requirements that each C instance should satisfy. First, they should be consistent. That is, the global condition should be satisfiable. Second, the queries should be satisfied by the C instance. And third, the C instance should be minimal, which means that if we remove any tuple from the C instance, it would lose either consistency or soundness. Moreover, we argue that an ideal solution consisting of a set of C instances should be complete. That is, all different ways to satisfy the query are captured by the solution. And minimal, there are non-redundant C instances, or say, every two C instances in the solution capture different ways to satisfy the query. Now we reach the core problem of building this framework. How do we decide if the instances are complete and not redundant? And how do we describe the ways that the query queue is satisfied? Before we dive into the answers to the previous questions, let's recap domain relational calculus used in this paper. DRC is equivalent to relational algebra and is basically the first logical formula consisting of quantifiers, operators, connectives, query variables, and relational atoms. For simplicity, we will only discuss binary tree representation of DRC queries. On this slide, we show the DRC query tree for both Q1 and Q2 and highlight the major differences in these two trees. Now we can discuss how to describe the ways that a query queue is satisfied in this tree representation. We make an analogy between queries and general programs and borrow the idea of coverage from software validation, which is used to denote which parts of the program are executed when running a test. Here, the coverage is the set of atoms in the query tree that are satisfied during the evaluation of the query on some concrete instance. And the coverage of this instance is the union of the coverage of the concrete instances it represents. This example illustrates the coverage of the instance I0 for the difference between wrong query Q1 and correct query Q2 in our motivating example, where only 2 leaf atoms are not covered. And for I1, compared to I0, the coverage of Q1 minus Q2 has an additional atom on the string comparison condition. Therefore, we can determine that these two instances, I0 and I1, capture the 2 different errors in Q1, since they have different coverage. And the notion of coverage can also help us measure the completeness of the instances. Now we can define our problem of query characterization. Given a DRC query queue, we want to find a set of instances such as every instance satisfies Q. There exists no other instances of the same coverage with smaller sizes. And for every pair of instances in the solution, there are no 2 instances of the same coverage. And the solution should be complete, which means that for any concrete instance K satisfying Q, there is an instance in the solution has the same coverage for Q. We also show that deciding whether the solution to this problem or even just satisfying instance exists is undecidable for general DRC queries. Therefore, our solution can guarantee soundness and minimality, but not completeness. Now we will show how to compute an exhaustive set of satisfying instances inspired by the classical chase procedure in data exchange, which transforms instances under a different schema given constraints, like this tuple generating dependency. Each chase step would enumerate a mapping edge from the variables in the dependency to label nonce in the current instance, and add the atom under the new mapping to build a new instance. Our procedure would generalize the constraints to DRC queries. Our chase step for the query queue would traverse the nodes in the syntax tree of queue, enumerates the mapping edge, and updates the set of label nonce during the traverse according to the quantifiers encountered. When reaching a leaf nodes in the query tree, we add the atom or atomic condition on the mapping edge to the current instance. After each step, we need to check if the resulting instance is valid. Here, I will briefly illustrate an example of how our chase procedure runs. Detailed description of the algorithm can be found in our paper. Given the query Q2, we start from empty label nonce and an empty instance. If there's no universal quantification of disjunction encountered during the traverse, it is trivial to create a label nonce to each domain, enumerate mapping from query variables to label nonce, and add leaf atoms to the instance under the mapping. and the challenging part is to handle universal quantification and disjunction. For universal quantification, besides enumerating all possible mappings from the quantified variable to label nonce, we also have the option to create a new label nonce, hence giving 2 branches for each quantified variable. For disjunction nodes, since the global condition of this instance is the conjunction of atoms, we need to reduce disjunctions into conjunctions during the traverse of the tree. This is done by considering all 3 possibilities that the conjunction can be evaluated to true. What I have described is the naive exhaustive search for C instances. Certainly, the branching may lead to undesirable performance. Hence, we proposed 2 optimizations. The first is to disallow the algorithm to add new label nonce for universal quantifiers. Hence, it prunes the branches by universal quantified variables, which will run faster, but will also lose some solutions for coverage. But then, we can force the algorithm to cover those atoms by adding them to the initial C instances and rerun the trace procedure. The other optimization is for conjunctive tree reduction. For every mapping edge enumerating during the chase, the naive algorithm repeats this tree reduction. One pruning method is to pre-compute the conjunctive trees and run the chase procedure on the trees with only conjunction but no disjunction. This may also lose some solutions or coverages, but in practice, it works well. Now we show the experimental results on queries we collected from the students' run queries in our database course. The figure on the left depicts the running time of our algorithms against the query size. We can see that the naive algorithm timeouts for almost every query with sizes greater than 20, while the optimized algorithm finished in 100 seconds for most cases. And the figure on the right shows the number of unique coverages of the C instances returned by each algorithm. Although the conjunctive tree optimization would fail to find some C instances, it returns at least the same number of coverages as other algorithms in most cases. We also conducted a user study to evaluate the effectiveness of these instances. We recruited 64 participants, and the task was to spot errors in 2 SQL queries. The treatment group sees C instances with example values, while the control group sees concrete value-only instances. Users are divided into 2 groups at random. Each group saw a different combination of queries and instances. The overall user performance shows that the concrete instance is already helpful. Only 31% of the undergraduate users fail to find an error. Going from left to right, we see a clear performance improvement among users who are shown C instances. The percentage of users failing to find an error goes down to 19%. And almost everyone was able to spot at least 1 error when given 2 instances. The majority of them indeed spot both errors in the query. However, no users were able to spot both errors with only 1 concrete instance. Here, I will conclude this talk. In this work, we proposed a query characterization framework using conditional instances, which is test instance independent, and we use the notion of coverage to capture different ways to satisfy a query. Although this problem is in general undecidable, we give efficient heuristics inspired by the chase procedure. And we did a user study to illustrate the effectiveness of using C instances to help users understand the queries. Thank you again for coming to this talk.